Before watching this video, make sure you have a good understanding of exponents and greatest common factor. If not, it is recommended that you watch those videos again. In this video, we will learn how to find the greatest common factor if the numbers are written using exponents. First, let's refresh our memories on some of the exponent rules. So if I have two numbers here, a times b, and they are raised to the power n, that is equal to a to the power n times b to the power n. And using numbers as an example, if I have 2 times 3 raised to the power 2, or to the second power, or squared, it's equivalent to 2 to the second power times 3 to the second power, or 2 squared times 3 squared. If I have a number and it's raised to the m power times that same number raised to the n power, that's equal to my number, and then I add my two exponents together, the m plus n. So in the case of using 2's, if I have 2 to the power 2 times 2 to the power 3, that equals 2 to the power 2 plus 3, or 2 to the 5th power. If I have a number and it's raised to a power and then I have parentheses around it and that's raised to another power, it's the same as the number and I multiply the two powers together. So in this example, it would be 2 squared, or 2 to the power 2, and then that is raised to the third power. Then I take my 2 and I multiply the 2 times 3, and I end up with 2 to the power 6. Finding the greatest common factor of numbers with exponents works mostly the same as with non-exponent numbers. You will remember that we find the greatest common factor by performing the prime factorization of each number. The difference is that in this example we're going to look at, the numbers are expressed using exponents. So I have a problem that tells me to find the greatest common factor of 6 squared and 8 squared. We're going to break this problem down into simple steps so that we'll just take it one step at a time. Make it easier for us to understand. So the first step is actually to just look at the numbers that we have, like our 6 and our 8, and think about those numbers for a minute. We want to find if either of these numbers is not in its prime factorization. And in both cases, 6 and 8 are not prime numbers. So you're looking at the numbers and finding numbers which are not written using prime factors. Both 6 and 8 in this case are not written using their prime factors. So the second step then is to perform the prime factorization on any numbers that aren't written as prime numbers. So let's look at the 6, and we'll do the prime factorization of 6. 6, and right now I'm just concentrating on the 6 and the 8. I'm not worrying about the exponents. I will put those back in when we start working through the problem. But we're just looking at our numbers 6 and 8. So 6 is divisible by 2. 6 divided by 2 equals 3. And so it's one simple step to the prime factorization of 6. 6 equals 2 times 3. And 2 and 3 are both prime numbers. So I can stop there at the 6 equals 2 times 3 level of my pyramid. With the 8 and the prime factorization of 8, we begin by dividing 8 divided by 2. And 8 is divisible by 2. 8 divided by 2 equals 4. So we have 2 times 4. 2 is already a prime number, so we'll leave that for our next level. But 4 then can be divided again by 2 to equal 2 times 2. So this can be divided, 4 divided by 2 equals 2 times 2. So 8 equals 2 times 2 times 2, which equals 2 to the third power, or 2 cubed we can say, or 2 to the power 3. And so now what we want to do is we want to take the numbers with the exponents in them that are in our problem, and we're going to substitute in for the 6, we're going to substitute a 2 times 3. For the 8, we're going to substitute a 2 to the 3rd power, or 2 cubed, and that way we'll have our number written in the prime factorization. So if I have my 6 squared and my 8 squared, then where I see a 6, I'm going to substitute 2 times 3. And I don't want to forget then now to raise that to the power 2. And then with my 8, where I have 8, I'm going to substitute a 2 cubed, and that's raised to the power 2. And so I'm going to draw a line here between the middle so that we can see that we're working on 2 different numbers. We're working on 6 squared and 8 squared. So for 6, let's work this out to the prime. We have it now in prime factorization, but we want it to look arranged a little bit differently. So we have 6 squared. We substituted 2 times 3 for 6 and squared that. And we know from our exponent rules that then this is the same as 2 squared times 3 squared. Now another way that I can write this in notation, so I should be putting equal signs here, another way that I can write this in notation is I can say this is the same as 2 squared 3 squared, and I don't even have to have that little x for multiplication in between the two. Sometimes you will see it with an x in between, sometimes you'll see it with a dot in between, and sometimes you'll simply see it like this. 2 squared, 3 squared, which is the same as 2 squared times 3 squared, or 2 to the power 2 times 3 to the power 2. So that is our prime factorization of 6 squared using exponents. And then for the 8 squared, we substituted a 2 to the 3rd power, or 2 cubed, or 2 to the power 3 for the 8. But then that 8 itself is squared, so we have to make sure we also raise this 2 to the 3rd power to the power 2 as well. And so with our rules of exponents, 2 to the power 3 raised to the power 2, we multiply our two exponents together. So this is the same then as 2 to the 3 times 2 power, or 2 to the 6th power. So now I have both of my numbers, both my 6 squared and my 8 squared, written in terms of prime factorization raised to exponents. So our third step then in finding the greatest common factor is that the greatest common factor is determined by finding the prime factors that are shared by both numbers. Right away, I can see that this number over here doesn't have the prime number 3 at all. So the prime number 3 is not shared by both numbers, so we're not going to have any 3 in there. The prime number 2 is shared by both factors. Now in this case, there are 2 2's, 2 times 2. Times 3 times 3, but there are 2 2's. In this case, there are 6 2's, 2 times 2 times 2 times 2 times 2 times 2. But we're only going to take the 2 2's that are shared by both of the numbers. So to find the greatest common factor, I take the prime number that they both have in common, and it's raised to the number of powers that they both have in common. So they both have 2 2's. This one has 4 more 2's, but I'm not going to worry about those because the only thing that they share is 2 2's. Now when I'm working on a problem that has exponents, the way to report my answer is to remain in exponents. So I would say in this problem that the greatest common factor, so find the greatest common factor of 6 squared and 8 squared, I would report my answer as 2 squared. The greatest common factor is 2 squared. Now we know that 2 squared equals 4, so it wouldn't be wrong to report the answer as 4. But when I have my numbers given using exponents, then the expectation is that I'm giving my answer using exponents as well. Let's look at a more complex example of finding the greatest common factor of numbers using exponents. So we are asked to find the greatest common factor of these three numbers. 4 to the 1 power times 5 to the 1 power times 6 to the 1 power times 9 to the 1 power. 2 to the 1 times 4 to the 1 times 5 squared times 9 to the 1. And 2 to the 1, 4 to the 1, 5 to the 1, and 9 to the 1 power. So our first step is we want to write each of these numbers in their prime number factorization. So we first want to look and see in each number which numbers are not in prime form yet. So we're just going to go one at a time through each of these, finding the primes. So let's start with 4 to the 1 power, 5 to the 1, 6 to the 1 power, and 9 raised to the power 1. So I can see here that 4 is not a prime number, 6 is not a prime number, and 9 is not a prime. So I want to write each of those numbers in their prime. So for 4, I'm going to rewrite my 4 as 2 squared. The prime factorization of 4 is 2 times 2, or 2 squared. So I'm going to rewrite the 4 as 2 squared and raise that to the 1 power. My 5 is already in prime, so I'm just going to leave it 5 to the 1 power. The prime factorization of 6 is 2 times 3. And so I'm going to replace the 6 with a 2 times 3 and raise that to the power 1. The prime factorization for 9 is 3 times 3, or 3 squared. So I'm going to replace my 9 with a 3 squared and raise that to the power 1. Now, using my exponent rules, I'm going to go through here and rewrite this as the prime bases, or the prime numbers, raised to their particular exponents. So in this first case, I've got 2 to the power 2 raised to the power 1. And so I multiply 2 times 1, which is 2, so 2 squared. And then 5 to the 1 is already in prime. And then 2 to the 1 times 3 to the 1, because this power 1 here gets distributed to both this 2 and this 3. So I can rewrite this as 2 to the 1 power, 3 to the 1 power. And then in this last case again, we have a number raised to the second power and then raised to the first power, and we multiply the 2 times 1 together, which equals 2, and write this as 3 squared, or 3 to the power 2. Now I can combine like primes, and so my 2 squared times 2 to the 1 power, I add my exponents, and that equals 2 to the power 3. For my prime 3, I have an exponent of 1 and an exponent of 2, and I can add those two together to get 3 to the power 3. And then I still have my 5 to the power 1. And it's good to write these in order of least to greatest with the primes. So this is the prime factorization of this number here. We're going to do the same thing now with our second number. 2 to the power 1, 4 to the power 1, 5 to the power 2, 9 to the power 1. So I can see in this case that my 2 is already a prime, the 4 is not a prime, and the 9 is not a prime number. So I need to substitute the 4 and the 9 with their prime factorizations. So I'll leave my 2 to the 1 power as it is. And then where there's a 4, I'm going to substitute that with 2 squared, which is the prime factorization of 4. So 2 squared, and that's raised then to the power 1. 5 is already a prime, and that's raised to the power 2. And then 9 is not a prime number, but we know that 9 equals 3 times 3. And so the prime factorization of 9 is 3 squared. So I can replace my 9 with a 3 squared and raise that to the power 1. My next step then is to go through and work out each of these to clean up the exponents. So I've got 2 to the 1, and then this 2 to the power 2 to the power 1. I multiply my 2 times 1, so I end up with 2, so 2 squared. 5 squared is already done. And then 3 to the power 2 to the power 1 is equal to 3 to the power 2, because I multiply these two exponents together, and 2 times 1 equals 2. So far I've got all my numbers down to their primes, but I need to combine any that are together. So I've got 2 2's here. This one's raised to the 1 power, this one's raised to the 2nd power, and so I add my exponents together. So that becomes 2 to the 3rd power. And then my 3 is to the 2nd power, or 3 squared. And then 5 squared is my last number, and that's my prime 5 raised to the 2nd power. So the prime factorization of 2 to the 1, 4 to the 1, 5 squared, 9 to the 1 is equal to 2 to the 3rd power, 3 raised to the 2nd power, and 5 raised to the power 2 as well. Now I'm going to do the same thing with this 4th number here, which is this 3rd number here. So we've done 1, 2, now we're doing our 3rd number, breaking it down to its prime factorization. So 2 to the 1, 4 to the 1, 5 to the 1, and 9 to the 1. So in this case 2 is already prime, so I can leave it how it is. 4 is not prime, but we know now that 4 equals 2 squared will be our substitution there, and our substitution for the 9 will be 3 squared. So I go through and start doing my substitutions. 2 to the 1 power, 2 squared, which equals 4 to the 1 power, 5 to the 1 power, already in prime, and then 9 is 3 squared to the power 1. My next step then is to clean up these exponents. So I've got 2 to the 1 is already done. 2 squared to the 1 power is 2 squared. 5 to the 1 power, and then 3 squared to the power 1 is 3 squared. So now I need to just combine my 2 2's, and my 3 and 5 are already just singular. So 2 to the 1 power times 2 to the 2 power, I add my exponents together, so it's 2 to the power 3. So 2 to the power 3, and then 3 to the power 2, and 5 to the 1 power. So I now have my 3 original numbers written in their prime factorizations using exponents. And what I want to do then for finding the greatest common factor of these 3 numbers is that I need to find the prime factors that all 3 of them share. And so this, I start by looking at my 2's. Well, all 3 of them actually share 2 to the 3rd power. So that one is simple. So let's see, I'm going to draw a line across here, and I'm going to put my answer of greatest common factor of these right here in this box. So for my prime factor 2, all 3 of my numbers share 2 to the power 3. So for my prime factor 2, I'm going to put a 3rd power. Now I move to my next prime factor, which is 3. So for my prime factor 3, this one has to the 3rd power, this one to the 2nd, and this one to the 2nd. So each of them shares 2 powers, 2, 2, 2, and 1 more. But they all 3 have 2 powers of 3 that they share. So I can use the 2nd power for my 3's. And then with the 5's, similarly, they have a little difference. They've got 5, we've got our 3 5s for our primes, but then this one's to the power 1, this one's to the power 2, and this is to the power 1. So even though this one has a second power of 5, all 3 of them share 5 to the power 1 as a common factor of that prime. So that is how I would leave my answer. I don't need to go through and multiply 2 times 2 times 2 times 3 times 3 times 5. But if I did, I would actually get the number 360. But I can leave my answer for greatest common factor of these numbers written with exponents. I can leave my answer in the exponent form. So 2 to the power 3, 3 to the power 2, and 5 to the power 1 is the greatest common factor of these 3 numbers.